Okay, hi everyone. Thank you so much for joining us tonight. We are excited to start this new program where we will bring someone in as a guest speaker every month, and they will present their career or their path leading up to their current career and so forth. We hope you guys will continue to join us for future presentations. If you guys have any questions, go ahead and type them in the large meeting room channel. We will open up Q&A towards the end of the presentation. Also, this session is being recorded, and we will provide the link after the presentation. In addition, everyone is welcome to share the story. Please go ahead and inform one of the admins or moderators or Jack or me, and we can set you up. Also, please share our Discord link. It is posted in the large meeting room. And again, thank you so much for coming out, and I hope you will learn something new tonight.
Okay. Do you want me to share my screen?
Yes, go ahead.
Let's see. Hopefully this works. So is my presentation showing?
So everyone just have to hit the watch stream, and you should be able to see his stream or his presentation.
Yeah. Okay. Let me know if it's not showing up.
I can see it right now.
Okay.
Me too. Yeah, we can see it.
Okay. All right. Well, I guess if we're ready to start, I guess my username everybody knows me by is Swayze Express. I've been part of the STEM Network Discord channel maybe for a year, most really. I actually don't remember how I found it or how I joined. I'm glad to be here. And I'm happy to at least share what I've been through and essentially where I am right now and the steps I took to get there. I think my path is pretty unorthodox, and it wasn't really clear what I wanted to do from the start. And so hopefully maybe at least one of you guys will have some sort of some information to take away from this, and hopefully it will help you in your career as well. So really I'm just going to go over my undergraduate career, graduate career, my current jobs, and the projects and research I work on, and following with any questions you guys have. Hopefully you have some answers from, but no promises there. So I currently I'm a mid-career electrical design engineer, electrical and battery engineer at Johnson Space Center here in Houston, Texas. But getting to this point has been a very, very tough road and a very long road. And I think it took, instead of 4 years to get here, just for undergraduate and 2 years of graduate school, it took more like 10 years or so. And still working towards where I want to be at. Not exactly there, but until then, it's been a back and forth between what I really want to do. And I think at this point I can say in my career, I know exactly what I want to do. And I know the exact steps I need to take. But it's all because of the experiences I had up to that point. So if we look at what I was doing during undergraduate, I went to a private university here in Houston, Texas, and I was a pre-med student studying biochemistry. I was really focused on going into neurology, just to be a neurologist. And that was the initial goal. That was the first thing I was thinking of out of high school. I think after 2 years being in, or 1.5, 2 years of being in that school, I wasn't doing well because I was trying to figure out, hey, what if I don't get into pre-med? I mean, I don't get into medical school. Do I need to have a backup plan? So I was thinking about going into biomedical engineering. The private school did not have a biomedical engineering program, but the university, my alma mater, which is University of Houston. And so I transferred over to University of Houston, still as a pre-med student studying biomedical engineering. At the time, I did not do much research on what biomedical research was, and I was just thinking about the cool things how I thought it would be. Very early on, I had a few issues at home that essentially it forced, not really forced, but I due to my irresponsibility and how I reacted to those events, I essentially was put on probation in engineering. So what that meant was that, hey, if by the next semester I don't have, I think it was a C plus or B minus in all my classes and more or above, that I will be essentially on academic suspension, which means you're kicked out of engineering school. So the following year, I was not able to do that. I still continued with just the hardships I was going through. I was still working at the time as well. And so I was not able to maintain those grades. And so I was essentially kicked out of engineering school. Given the nature of that suspension, it was tough because at the time I was looking into, I was like, I knew that I couldn't go to pre-med anymore. With the grades I have, my GPA, there's no medical school that would take me in. I was roughly around a 1.6 GPA at that time. And obviously coming back from that, I was basically sophomore year. So coming back with 2 years, is not going to help me at all. So medical school was gone. To me, engineering was gone. And I really didn't know what else I wanted to do because anything I was thinking of is basically gone for me. During that time, I was reading a lot of these little posts on the walls in our student centers, and one of them was talking about they needing any majors to join this group to do a research project for NASA Wallops facility. So they do balloon studies. So I just reached out. I reached out, and the professor, he's still there, Dr. Edgar Bering. He essentially took us in. He did not really look into if I was in engineering or not, or what my grades were. He was more so focused on just helping students out with this sort of opportunity. I'm thankful I actually looked at those banners, because if I did not, I don't think I would be here where I am today. Because that was really the only opportunity I had to essentially kick back myself into gear. Following that, I was able to essentially get motivated enough to push myself further and study more to ace all my classes and get back into the engineering program. So they allowed me back in because I was able to prove that I was able to maintain a B or higher in all my classes for a given semester after a year. And so going back into engineering, I realized how much I've messed up, how much of it is irreversible. And so I quit my job, and I essentially dedicated all day, all night, just to studying and finishing off the semester strong. So I would go to school around 5 a.m. and I would leave around midnight or 1 a.m. I'll go back home and just studying the whole time. I gave up pre-med because it was not attainable anymore. But after being in engineering for so long, I realized this is actually where my passion actually was. So around 2016, I graduated a biomedical degree in neuroengineering with a biology minor. Took me about 5.5 years, and I graduated with almost a 2.7 GPA. The thing was that towards my end of my undergraduate, I realized the biomedical degree I was going forward with is not really useful, in the sense that I did not learn anything. And the reason I knew this because when in that program that I was in, there was a lot of electrical engineering classes you have to take as part of the program. And when I was in those classes, I realized how much more other students know and how much detail to go into. And so what I had to do was basically appeal as much as I could to change my biomedical classes to match electrical engineering classes. So I would say about 50% of my classes when I graduated were electrical engineering. And so I knew essentially that I should have, if I could go back, I would have just done a straight classical engineering program. But I wasn't able to do so. And due to my grades and my lack of experience, I was not able to be part of any internships, and my capstone project was not really anything noteworthy. All I had was essentially the NASA research project. I was in that program for about 4 years, and I'm still in it right now as a mentor. But that program basically laid the foundation of where I am today, because I was looking at working in the industry versus working in academia or research, and so being in that research environment basically kind of paved the way for me to be more towards the research side. Hence, I went back to school almost immediately after. And I went for my master's in electrical engineering. However, there was a year between going from undergrad to master's, and that's where I got my first job at a hospital working as a heart pump specialist. This was a gruesome period because I would work night shifts, 12-hour shifts. I would go in at 6 p.m. I would come out at 7 a.m. and go straight to the university and have classes from 8 till sometimes 4 and 5, and then start my shift again. So I would probably get like 30 minutes to an hour of sleep, and then during downtime, I would study for my classes. But at this point, I knew the worth of education, and I knew the worth of the skills that I need to be learning. What I was essentially doing at this point was going on LinkedIn or talking to any researcher I know or any professor I know, and I asked them how they got to where they are, what classes would they think is better for the area of research I want to go into, and so forth. And so I used those as a little mapping stone to essentially pave what I need to take rather than what I want to do. And so I was taking it as a more of a systematic approach to my education than I was in my undergraduate. So during my grad school, I was working towards a master's in control theory, particularly modern control theory and power electronics. I finished that around December of 2020, and then I started a new master's at Georgia Tech, working on a master's in machine learning and analytics. This is not me changing my career path. It's more so just giving me a structured program to help me learn what I need additional to control theory for my research. And so this is more of a supplement to my first master's, and hopefully I can finish it and it would actually supplement what I need. So far it's been pretty good. And basically that leads me to where I am today. Right now I am working as a battery algorithm engineer and a battery management system designer. I do the electronics design and the algorithms for the battery chargers here at Johnson Space Center. Until maybe I think this January of this year, I was working as a battery abuse tester. So what we would do is essentially what you see on the right-hand side. We abuse the batteries that go on any NASA project that has a battery powered system, or we just run experiments on how to design a battery pack. So we'd run either mechanical stress tests, such as like crushing the batteries, penetrating the batteries, heating the batteries with lasers or wire heaters. We would vibrate them and shake them until they blow up. Things like that, things of that nature. We will also use electrical abuses, so we do life cycle testing. That means we charge and discharge aggressively for the length of the battery's life to see how long it can last, how does it react to different dynamics and load transients that it sees. And we also just do basic testing to see how it operates within the conditions of for the mission that it's going to go on to. So I've been working on the Viper rover, which is the rover that goes on Mars to look for water. I've been working on the XCMU battery pack for the spacesuits, the new spacesuits. And I've been working on the VPS project recently, and that's the one that that's for the Lunar Lander project. So it's for the suits that will be used for astronauts that go on the lunar surface. It has to be different because of the radiation levels. So is this where I want to be? I think so. I think coming from where I was starting at, I really didn't have any direction. But coming to this job, I realized how much of what I've studied matters, and I think seeing that worth has really solidified what I really want to do now. I do see myself pursuing a career in battery engineering for the rest of my life. and I do see myself remaining in a technical field as well. So I know that a lot of people do like to take a master's for just like more of like a promotion towards a management role. I don't see myself doing that, and maybe down the road that will change. But for now, I do see myself remaining in this sort of kind of work. So some of the projects I was working on in my graduate career and also at work were, well, let me start with the undergraduate parts. The balloon research we were doing was for heliophysics. We were studying the radiation belts, and we were studying the ionosphere that surrounds the Earth. And we would be traveling to different countries and states, and we would be flying our payloads, which we would design in-house at U of H, and essentially flying up in space and see to do different experiments. This helped because I was exposed to actual design and research, meaning, what do I want to do? Okay, I found out I want to do A, B, and C experiments. How do I actually do them? That means I have to go do about 6 months of research, maybe a year of research. I finally got the research down. Now I talk with my team. How do we actually approach it? How do we actually design a prototype? What's this? Who's going to draw the schematics? How is it going to look like? And then designing a prototype, testing a prototype, fabricating the actual payload, flying the payload, doing the data analysis. So these were things that you do as an engineer in a professional setting, but you don't really do it within classes. And so my biggest pet peeve with classes was that I was not exposed to this sort of work. You do some lab work here and there, and they tell you that you're good to go, and you go to your next semester. Having this kind of experience was very valuable, and I think that if anybody is taking classes, they should always look for any sort of information online about that class and see if it's project-based or not. That's what I was doing in graduate school. When I was in graduate school, I was not doing a thesis per se, but I was looking at which professors are going to ask me to do a course project, at least a course project, and so that I can actually work on something rather than just studying the material and then moving on. Just a quick little clip to explain what we're doing. So essentially, what you see here is a high altitude balloon, zero pressure balloon. It's attached to a bunch of different radars, sensors. These are squibs. These squibs are explosives to blow up the balloon once it's reached its final destination. So it comes back down. We have a parachute, and then I'm holding on to the actual payload with the GoPro on it. So I don't know if anybody will hear it.
Like, I honestly missed that shot like probably 9 out of 10 times.
Don't though.
Yeah, you do.
No, not 9 out of 10 times. I at least go 50-50. If not 60-40.
I mean,
So-
my point is it's a hard shot to hit. If you go to the net and turn around, then all of a sudden you got the good angle, and then yeah.
So this was in Kiruna, Sweden, and this shot is right when we got to the altitude we wanted to. This is basically the D layer of the ionosphere. Right below us is the surface of the Earth. So we traveled to Sweden twice to work with Dartmouth College, and they were doing their projects, and they said that we can piggyback on their experiments. Sorry, whoops. And so that was that. After a few years of that, I realized this is not really what I want to do, but I learned a lot of skills that I can transfer over to something else. So you can see up to this point, I wasn't really focused on a certain area. I was just focused on getting the skills I need for my career trajectory. During my actual research for graduate school, I worked with a professor to essentially take my course project to become more of a thesis. I did not do an official thesis. Let me say that. I did not do a thesis defense or anything. However, this was work related to the professor's lab, and they needed students to help. And I offered just assistance to essentially carry out this project, but I was not doing this for a thesis. We are working on a publication currently, and the whole premise of this project was to essentially take biosignals from a person. So we were using EMG. That's the signals from your muscles. We take that, and that goes to a wearable device. So we have some sort of let's say for example a watch, reading the responses from your muscle activity, we relate that to a person's emotional valence. So emotional valence is how the magnitude of being very happy or very depressed. And so what we're trying to do is regulate that. We're trying to help a patient to be able to regulate that on their own. So what we have is a closed loop, feedback loop, control loop, in a sense. What we do is basically we take the EMG signals, we process it, we get our features. We have continuous features, binary features. We run this through an EM algorithm. EM will help us to essentially identify all of our parameter needs for our models. So all of our models are going to be identified, all their parameters will be identified, and the states. So the state is what is the current, what is the current response of your system? Our system is the human body, and we're tracking the emotional valence. So what we're doing is essentially looking at what is their, what kind of, how is the patient feeling, and based on that, we give a feedback. So maybe dim the lights or play a certain song or something. That part hasn't been identified yet, and we have this feedback loop to keep doing that until someone has a positive emotional valence, meaning they're more happy. So if you look at the bottom graphs, where it's shaded gray, that's when the person's feeling distraught or angry or depressed. And the ones that are not shaded is when it's low valence, meaning the patient is feeling pretty set. And so what we're doing, we're simulating, hey, if we were to excite the patient, meaning make them, sorry, I said that in reverse. High valence means they're very excited, they're very happy, and a low valence means they're very depressed. So if we want to inhibit the patient from being happy, we would see that during the simulating from low valence to high valence, we were trying to track the person and then make them happier. So in inhibition, during the high valence part, we see that there's lower spikes and the actual states of our system have mitigated more than it should. So during the parts where they would be really happy without the wearable device, they were very excited with our wearable device. As you can see in this section right here, they were you would say less excited or less happy. And in the meantime, we have excitation. If we were to excite them more than they are, so we would say that during the point without the device, if they were to be very happy, you can see on the top graph, on the top left part of the graph, that's what they were at without the actual device. If we would add the device and excite the patient even more, we were able to get a pretty significant increase in our emotional valence. So the results are working. We're still working on the paper right now. There's a lot of information on here. I don't really want to go into it. If anybody's interested, I'm open to talk about this more. But this was something I was really grateful for because I was able to essentially work on a research project with the publication. That's something I haven't experienced before, and I'm glad I chose this class because if I did not, the class I would have taken instead of this was just a course. It was notes, homework, test, and exam. That was it. I would be missing out on this. So I'm grateful actually for working on that. Some of the course projects I've done has been related to lunar lander projects and power electronics, and specifically I'm working on control theory. So on the lunar lander side, I was working on developing nonlinear controls to help a lander land on the moon based on the two phases. There's a approaching phase which is nonlinear. So as the lunar lander is approaching the moon, it goes to a certain trajectory. And then when it's 30 meters above the moon's surface, it has a linear trajectory. So we solve it in two different formats. Here, if anybody's interested, I can go into more details, but we used a SDR controller and an LQR controller. This helps the lunar lander to position itself when it needs to, and when to actually thrust the boosters on the most optimal way, so that it minimizes the time it takes to get there and also the amount of fuel that is used. On the left-hand side, I was looking at using a MPC controller, which is a model predictive controller. This is something that we use for any sort of model-based design. I modeled a SEPIC converter. A SEPIC converter is a similar to a buck boost, meaning either it can boost your output or it can step it down or buck it. However, it's essentially a buck boost converter plus a boost converter. So what this does, it helps you reinvert the output. You have a positive to negative output. And so we use SEPIC converters and battery chargers a lot. And so I was thinking about if we were to have a reference voltage to follow, if our output was to track a certain voltage and that voltage was to fluctuate a lot, how would most converters will not be able to actually follow that kind of trajectory. So essentially what I did was I was adding random step inputs. Where's my mouse? So the blue graph on the left, my mouse. Blue graph left was random step inputs I was inputting to the reference. And so on the right-hand side, I was comparing the MPC controller and the LQR controller. The black line shows how fast and how quickly and how accurately the MPC was actually able to follow these sudden changes. So that tells me that with a MPC controller, I can optimally regulate the output of a SEPIC converter properly in the situation where my reference signal, wherever it's coming from, can be if it's witnessing any sort of noise or any sort of input from something else, the output of my converter will not be unstable and basically burn up the actual circuit. So this is something I'm actually working on at work right now as well for one of our designs. So it has some good carryover. However, this was just a course project, not a thing like a research. But currently at work, I'm working on what I call battery algorithms, battery algorithm, battery modeling, battery control. This is a very new field. I would say it's been around for about 10 years, but it's really ramped up within the last 2 years. If you recall, if anybody has an iPhone, and I don't know if Android does it, if you have an iPhone and you're charging your phone, and let's say you use your alarms on your phone, if you ever noticed that towards a certain time of the day, if you're charging it, it would say the charging has stopped, and we will resume it once you wake up or near the time that you wake up. So let's say if I sleep at 11 for every day, the battery charger inside the iPhone would say, okay, at 11 I'll start charging, but I'll stop around 3 a.m. I know that he wakes up at 5 a.m. So I'll resume my charging at 4 a.m. So by 5 a.m. when he wakes up, it's gonna be fully charged. What this does is essentially it extends the battery's life, and it makes it safer. And I'll explain that in a bit. Batteries, if you look at the top left corner, batteries work in a very particular manner, and they're very complex. So talking about lithium-ion batteries, the green circles and these tetrahedral structures, these are your active material. Active materials are where they're like shelves, where the red circles are your lithium ions. These are shelves where lithium ions go and they're lodged between. And so the more red ions that are lodged between one side, it's either charged or discharged, right? So if there's more lithium ions lodged in the anode side within the tetrahedral, you have a discharged battery. When you're charging it, they all move towards to the cathode where the green spheres are, and they're lodged within the green spheres, and that means it's fully charged. And so a battery is both a mechanical, chemical, and electrical problem. This back and forth of lithium ions is introducing a lot of mechanical stress and chemical stress. Chemical, because the ions are free when they're moving around. There are a lot of other chemicals inside a battery that can stack those lithium ions. The less lithium ions in a battery, the less capacity it has over time. And so as time goes on, your battery becomes weaker and weaker and weaker. Meaning it charges, it can't charge as fast as it used to, or it would charge as fast, but it won't hold the same amount of charge it used to. On the other hand, this back and forth of lithium ions getting lodged between these layers causes mechanical stress. It causes cracks within the actual anode and cathodes. When there's cracks within those layers, they can't hold lithium ions. So what happens is that these lithium ions have nowhere to bind. They're just floating around. Well, if they're floating around, what happens is that the lithium ions basically start to stack up in each other. And when they're stacking up in each other, there's a possibility that they can short within the battery and the battery would explode. I don't know if you remember, Samsung had that issue with their cell phones where it was blowing up in people's, in their pockets. It was basically, they were thinking about why it was happening, and they did not design the battery well enough. They were getting what we call lithium dendrites. Lithium dendrites are like little teeth, that are formed by a stack of lithium ions, and they puncture the separator. The separator is what allows us to keep division between our positive and negative. If you cause a crack within that, you cause a short and the batteries start to blow up. So what I do is essentially I model this. I use dynamical or partial differential equations. As you can see on the right-hand side, I model all the different processes inside of a battery. I take this. I also run tests on the battery, so I discharge them in particular ways. So I can extract values from these to develop what I call state space models. Essentially, these are equations that describe the dynamics of the system through states. So using that, I can do predictions of how long is this battery going to last, how many more cycles can I charge. I can include it in power electronics, so such as this resonant converter. I can say, hey, instead of just switching the power converter on and off based on the converter itself and just information that we have from experimentation, use the actual inherent models of the battery and charge based on that. What this allows me to do is I can tell the converters, here are some constraints. I don't want you to charge in this certain way when the internal resistance of a battery is so much. So batteries, you can only measure 2 or 3 things. You can measure the voltage, the current through it, and the power and the temperature of the battery. So when you only have 3 measurements, it's hard to actually tell the converter what to do. So we need to have these sort of models. Right now, I'm working on a prediction algorithm where I am basically predicting the amount of cycles left in a battery's lifetime. I've presented this and I proposed this at NASA. Hopefully, if it goes through, we can actually implement it, which goes to my next point. I think one of the biggest helps things that helped me throughout my undergraduate and graduate career and at work is asking questions and being proactive as much as you can. So while I was an undergraduate, when I was admitted back into the engineering school, I essentially was working with the professor day and night. I was in their office every single day. If I didn't even have a question, I will still go. And say, hi, this is the work I was doing. What do you think? And from there would be questions I will come up with on the spot. I kept doing that over and over again. I would ask anybody I thought knew the answer. I would say, hey, how would you do this? Why did you do this? And so the real key is why. Understanding why you're doing something is very crucial. And towards the end, there was someone in one of my labs. He was a PhD student. He asked me. He told me that if I'm thinking about a PhD, there's a really good quote he told me. I never forget it to this day. He said, "Do you want to live to work comfortably or work to live comfortably?" So essentially, do you see yourself trying to just find a job, pays well, you're doing fine, and then you can live comfortably, or do you want to actually is the work that you want to do what that will make your life comfortable? So is the work that you're going to be doing what's going to make your life comfortable, or is just the little small aspects of work that can make your life comfortable in terms of pay and location and stuff like that? And so that really helped me decide what I want to do in my future. I'm very interested in being highly technical and eventually maybe even go back for a PhD because I can't really be content with not knowing. It's some sort of a kind of, sometimes it's a downfall because I can't focus on one thing and move on to the next when I just get the answer and move on. I have to exactly know every single detail about it. So I lose a lot of time sometimes, getting distracted like that. So to me, that question really helped me, decide what I want to do with my future. Being proactive in classes and workplace, like I said, keeping ask questions if you're paying because you're paying tuition to do so. That's the whole point of school. You can learn everything you're being taught in textbooks. You can buy those textbooks without going to class. You can go to these online lectures on Coursera. That's not the reason you're paying the school. You're paying the school for one, recognition and a degree, but two is to have the resource of a teacher to ask. I can't ask Andrew from Coursera on his machine learning class questions. He's just giving me the notes and the homework, and that's it. I can ask people on Reddit, but they're not really professors. I need to talk to someone that's been doing it for years and years and decades. So ask questions as much as you can. For example, one of my classes, when the class will be over, I essentially would stay back with the professors asking different questions, making sure I understood every single thing I wrote down. Even if this was it was a night class, even though they might have been annoyed, I didn't really care, because I have their job and I'm paying for it. So I made sure I understood everything before I left class. The another thing that helped me was when I would have study groups, I told myself I want to be the person that when someone asks me a question, I'm able to actually answer it without looking at my textbook. So I studied in a way where my studying was more like teaching, teaching people how to do a problem or why you're doing a problem really helped me ingrain what I've known over my courses. And then I think the last takeaway would be don't look at where you are right now and say this is how my career is going to go. There's always ways around it. I had 3 different jobs, none of them related to batteries or electrical engineering. I was kicked out of engineering. I was in pre-med. I was in biochem. I was in biomedical, and now I'm in electrical and now computer science. So all these different outlets are there. And it was not really clear where I wanted to be. What I was doing was basically trying to pinpoint the skills I need instead. I think if you go in and you're looking towards to see if, I want to be in this one area, let me just go that based on the name so if I want to go into electrical engineering, to work on batteries, if I could go back, I would go back and do a chemical or mechanical engineering. I shouldn't look at batteries or electrical. I should go to electrical engineering. I need to look at exactly what skills I need. And so going on LinkedIn helped me a lot. Going on LinkedIn, seeing people that work in the battery field, I see that what kind of skills they have, what kind of research they did, what kind of projects they've done. I would read their papers and see what kind of keywords they're talking about. What kind of theory was this? And I'll type in that theory, and I would see that, hey, this is taught in the mechanical department, or this is taught in the industrial department. That's how I essentially tailored my career towards the end, to be able to be where I am at. I think at this point I can comfortably say that I am content with where I am, and I can essentially tailor my resumes and my job searches in the future, want to be much more precise. And so I hope that anybody watching this, sorry if I've been jumping back and forth, but hopefully through questioning, afterwards we can discuss and see if anybody is in the same kind of situation, and they can pinpoint exactly what they need to go forward with their careers, so that they can tailor without being, just randomly applying and randomly moving forward. Having a sense of direction is really, really important. I think that's it. Anybody interested in the battery algorithm stuff, I have a presentation I gave for the control theory Discord. I have the link here, but I can provide it in Discord as well if anybody's interested. And that's it. If anybody has any questions or concerns, just let me know.
Hey, Swayze, this is Robbie Kings, aka Robot, one of the admins here.
Oh, sure. Hey, what's up?
So, one of the first questions is a universal mistake. A universal mistake says, do you have to write failure analysis papers?
I would need a definition of failure analysis. Yeah, I mean, we do write exactly a report of why a battery or not battery, sorry, why a system did not work the way it did. We write risk analysis. So what are the risks going into the project? So mission risks, we also write safety risk for the personnel, and we also write failure analysis afterwards when the testing is done. Essentially, it's an overview of what our results are. Mhm. Mm. Mm. Yeah. So yeah, if in that case, yeah, we do write failure analysis, and we actually present it to both the department, and we also present it to any battery conferences that come up, because a lot of our work we're doing is still it's novel within the field. But yeah, any testing we do, regardless if it's mechanical or chemical or electrical, we do write failure analysis, because that's the whole premise of our department. We're doing abuse testing, not really battery testing itself. I don't know if that answered your question.
Yeah, the next question is from Barwachi Kana. I think you're looking at it right there.
Yeah, specifically. So mentioned you prefer having intern projects for classes. How do you go about choosing working for projects, specifically doing projects in a class where you have no prior experience with them? Yeah, exactly. So two things. This is a really good question, because I struggle with this a lot. So I'm going to start with the last part. So how do you go about doing a project when you have no experience in the material? Every single project that I've shown you on this in this PowerPoint, and anything I've done outside, I have zero experience going in. Especially the research I was doing in undergraduate. That took me about a year just to understand what I'm looking at. I say to anybody that wants to be in a technical field, don't think about it, because you want to be in that position. That's the whole point of being an engineer, to be able to work on problems that you don't know the answer to. So that part, as much as you can, don't worry about it. I know that you're thinking about it as, hey, I need to be finished within a certain amount of time, and I need to be getting a good grade on it so that I can actually pass the class. No matter what you pick, you're going to get a solution in the end. Why? Because if we go to your first question, how do you go by choosing an idea? Talk to a professor. Professors are always open to giving you ideas. If they see if you go in there with saying, I don't know what to do, give me an idea, they're not going to help you. But if you show some effort thinking, hey, I'm thinking of doing so and so and so, which is what I do at every project I had. I would go to the professor and say, this is what I found online. And usually that means I go on Instructables or Hackaday or any sort of like reports I find online through whatever, these random sites that people just like upload their work, like random lab reports from a class or something. I find those. I'm like, that'll be pretty interesting. Let me expand on this, for example. And so I will take that to the professor, and we will go over it and say, hey, what do you think about this? And usually what they always tell me is that, no, this is too much for this class, or you're not going to be able to finish. This is too easy. Here, just work on this one aspect of it. For example, I had another example is like I had a power electronics professor. I was the only person in the class that did not have power electronics experience beforehand. Everybody in the class was working as a power electronics engineer. I was still in the hospital. So I'm still looking at everything like as if it's a new thing. I essentially went in there. I just told him that I was like, I have no idea what I'm looking at still. And as you can see from my grades and the exams and stuff, it's not going well. Can you help me direct me towards a project? And he's like, oh, well, I have this project idea, this research idea that just came through from the Navy. And we're looking towards to do this whole project. Maybe you can just focus on this one little small aspect, and I think you should be able to do it. And if you need any help, just come through. We will sit down and work it together. And that's what I was doing. I was going back to his office every day. I was like, I don't know where to start. He was like, well, all right, this should be basically your first step. He wouldn't tell me exactly what to do, but he's like, just think about it like this. And I'll go back and I'll go on Google and just keep studying and trying to read up on similar projects. But really work with the TAs, work with the professor to actually come up with an idea. Now, if you're experienced, so towards the end of my graduate career, what I was doing is essentially I go on Google Scholar and I type in keywords such as like if I'm like for machine learning, I would type in like SVM, or I would type in gradient descent or something like that, and I would say I want to do that for batteries. So I would type in gradient descent, batteries, lithium ion, estimation, prediction. I write all these little keywords, and then I have, tons of papers come up. And essentially, I just start reading them one by one and then say, hey, I could probably replicate this. And so what I will do is I will replicate the ones I think I can do. Once I replicate it, now I know it gives me a confidence boost. I essentially have this project in front of me. I basically replicated their project. Now, what can I add to this to make it my own? Or even if it's an incremental change, which on a side note, that's what most research is getting incremental changes in the field. But even if it's a small change from the original, it's something that I've learned. Maybe it's nothing. I'm not trying to make anything new. I'm not trying to invent something. But I was able to get the skill set needed to do this sort of project and move on. Whether or not the teacher wants that or not, too bad, because that's what I needed. I know, so I'm thinking about it for my own sake.
All right. Again, user at Universal Mistake he noticed that you use two-dimensional arrays in your questions, and he's asking what numerical methods are involved here. And if so, which ones do you use?
Dimensional arrays and not
he
sure.
might have been referencing one of the slides where you were using two-dimensional arrays.
I'm not exactly sure. Let me see. Share my screen. Is my screen still sharing? I'm not sure.
Yeah, we can see it.
Probably the battery stuff, because he was asking about the battery stuff. Two-dimensional, I don't know. Maybe if it's about the battery stuff, there is nothing two-dimensional. These are multi-dimensional. Battery modeling is a multi-scale, multi-dimensional nonlinear problem. The battery model, the one I work with, is called P2D. That is at a minimum 30 parameters. I've seen it go up to about 50 parameters and more. So we use approximation methods to solve them. So such as things such as like Galerkin, PADE, Taylor series expansions, these sort of things to simplify these expressions and then implement them on microcontrollers or simulation files. But the actual arrays and stuff used in battery modeling is very high dimensional and multi-scale. So every parts of a battery it works on a different scale length. We go from nanometers all the way to an actual battery pack, which is measured in meters. So you have this sort of dimensionality problem that you have to deal with. And so the arrays and stuff are much larger than two-dimensional.
Awesome. Let me go back to the questions here. Lil Grizzly asks, he or she is starting their full-time internship after 11 months of not having full-time work, and they're getting ready to study for the PE in the fall. Now, they're asking, what did you have to do to be readmitted into the engineering program, and what advice would you give?
So the issue was that I think I was a 2.5 GPA. I was on probation. After I was on probation, I needed to make a B in every class so I can stay on probation for one more semester. And then if I do the same thing again, I would continue in engineering. Well, the first time I wasn't able to keep a B in every class. I'll just say it. My father passed away early on when I joined the new school, and my reaction to it wasn't really set. So it wasn't really proper. So I wasn't able to keep up. And so essentially what happened, I failed classes. I had, I think, 4 or 5 Fs on my transcript, and that really dragged my GPA down. And so the time when I was on probation, I failed again. My GPA went down to like 1.5 or something, and I was suspended. The condition was that I am not allowed to take any engineering classes for a year. And then after a year, I can reapply, and then maybe they'll let me in, maybe not. And so what happened was that I essentially waited a year. I took things like history and philosophy classes and stuff just to fill out my electives. And at the same time, talking with my family, thinking like, what's the next step? They were obviously not really happy about it, but there was nothing else we could do. I didn't think I would be going back into engineering. So what happened was when I reapplied for engineering, I said, look, my grades within this 1 year, they've been good. It wasn't just electives. I was taking stuff like biochemistry and organics. So there was some technical classes that I was showing them like, this is the reason I was suspended. These are what I basically had like a report for the dean. These are my grades. This is how I study for them. And this is how I'm going to do it when I am readmitted. So they said, okay, conditionally you're back in. So once I'm back in, I had to maintain a B in every class for that one semester. And what happened was that I essentially got a C plus in one of my classes. It was in mechanics. And so I talked to the professor. Obviously, they said, no, we can't do anything. But the reason they talked to the dean for me was that I was very proactive in the class. I was sitting in the front, asking questions every 5 minutes. I was that student after going back in. So I was very proactive. I was always in their office asking questions. They saw the effort, and seeing that effort basically made her go back to the dean and say, hey, he might have gotten a C plus, but I think it'll be worthy to bring him back in because he put in the effort for it, and here's the proof for it. And so that's essentially why I was let back in. And so if someone is in the same position, there's no other way about it but to really work. And by that, what I mean is don't just do the homeworks. Don't just study for the test. That's what I was doing beforehand. I was studying just for the test, how to pass the test and move on. I put that to the side. I didn't think about grades anymore. I was thinking about, I need to understand this fully. What I would do is I would do the homeworks. I would go online, look for more problems. I would go on forums like Reddit, subreddits for engineering, and I'll look for these kind of problems that are similar to my homework, and I would try to answer that. I would try to help people with that online. I told myself, if I'm able to do that, then I've understood the material. What that led to is that when I go on exams for these classes, I would have cheat sheets, but I would never use them because I've practiced it so much that it's just I remember everything on those cheat sheets that I had. So at that point, I was able to prove to the school that I'm actually capable of completing engineering. So I think anybody in that kind of position, they really have to put in the effort. It's I was working at the same time, so there's a lot of excuses we can give. I think whatever it is, at this point you have to just say, okay, this is it, and I have to actually work through it. There's really no other way around it. This is not a position anybody you want to be in. So the quicker you act and the more you act, the better it is for you.
Okay. Chase asks, when reaching out to people, particularly when looking to move forward in your career, what things have stood out to you that say, I definitely should or shouldn't talk to this person.
Oh, okay. So I guess a good example is what I am doing currently at work. For the last 2 years, I was working as a test engineer, and as of 2 months ago, I'm working as a electronics design engineer. And so what I did was during these 2 years, when the design team would come over, I was basically looking at who's really calling the shots here. They had engineers that would come in and they just do the work and they leave. And there's people that would come in with presentations and, hey, I brought in funding for this. Hey, I was talking to so-and-so who was the head of so-and-so. And so what I would do is essentially, I'll talk to them, say, hi, how are you? My name is this. I just joined. I didn't really care if I should talk to them or not. I just introduced myself. And over time, they would, with just by nature of conversation, things would come up like, oh, where'd you go to school? What did you study? Oh, you're doing research. What's your research in? Battery algorithms. What are battery algorithms? Oh, this so-and-so, you can do so-and-so. Oh, we could use this for our project A, B, and C. And so those little cues told me, hey, I need to just talk to these people more. So what happens is that I didn't ask for positions or open positions or anything. What I would do is say, okay, they would email me saying, can you do this test for us? I'll say yes, and then I'll ask them why. What are we trying to look for? Why not just do this? Hey, I saw this same kind of test on this research paper. What if we do it like them? And that conversation is something that they remember. So the reason I have the current job I have is because they were looking for an engineer and they couldn't find one until someone says, the person I was talking to was like, hey, do you guys know Arian? He's the one that was presenting those stuff on, for example, battery algorithms. And so they was, oh, okay, yeah, just sure, bring him in. And so that's essentially how I've been attacking it. I haven't really been going out asking people, hey, how'd you get where you are and stuff like that, even though I think people should. I have a very bad imposter syndrome, so I cower in that aspect. If I did not have that, yeah, I would definitely just reach out to anybody. It doesn't matter who it is on LinkedIn. I tell people engineers have a really big ego. So when you ask them, hey, you seem very successful. I really want to be in the same position you are. How'd you get there? They love talking about themselves. So, definitely reach out to people on LinkedIn. It's just a quick message. They either reply or don't. But if you're working currently and you're trying to move up, I think it's better to prove yourself rather than ask for it. So in the last 2 years, I've been giving presentations, trying to ask different actual questions about the test and things like that, just to prove myself. So they don't really have to interview me or anything like that. They know exactly how I work. And it's just the easier movement for someone.
Awesome.
Yeah.
Schrodinger's mouse asks, how important is the PE or FE license in your industry?
I would say it's not important at all, because I am not working on any civil sort of projects. I'm not working on civilian buildings or civilian infrastructures, and I'm not working on anything related to the body. Even though I think even medical engineering stuff doesn't require FE or PE. So for me, since I'm strictly trying to stay in research, and sort of in this prototyping research area, I don't think so. From what I'm seeing, I don't need a PE or a FE. Now, if you were to work on things outside of research, especially if civilians are involved, that's where I think it wouldn't hurt to get a FE or PE. I think anybody that is just graduating should just do the FE. I was very lazy and I did not. And now looking back at the books, I'm like, I don't know if I remember all of this. I don't have time for this. But if you're just graduating, just do it. It doesn't matter if you need it or not. It doesn't hurt. And I think if you can just do it, when you graduate, just do it and get it. Either it helps or it doesn't. But it doesn't, there's no negative side effect to getting one. But for me specifically, I do not need a FE or PE.
Great. Chase asks, what do you think most helped you in finding your career path, whether it be time, surety, or diversity of experience, or was it something else?
Diversity, and also mainly diversity, being exposed to different parts of engineering. I realized what I remembered more, the things I was remembering more and thinking about throughout the day. It was a clear indication that's where I wanted to be. But also just reading on current research on certain topics and looking at the hype behind it kind of motivates me. I don't really like going by hype, but I think if someone is trying to look for where they want to be at, maybe that's something they can look at, is that they look at the current research going on for a certain field, realizing, hey, this is pretty new, and I would like to be part of it, rather than being in a position where everything that you're going to be doing is already set in stone, and there's really no more innovation within it. That's why I'm here. What I've seen is that basically people either at my stage or even much more senior than me, everybody's on the same page. So I think that's really interesting. But I wouldn't be here if it wasn't for the diversity in terms of projects and the different majors I've been put through. So diversity, I think, helps the best. If you're able to find project-based classes, it helps a lot to, help you think about, do I want to do this forever or not? For a pretty long time, at least.
Okay, the next question is from Mankey of War, and they ask, was it difficult to get into your first master's program, and what factors did your school take into consideration when accepting?
Yeah, right before I graduated in 2016, May 2016, and then I applied for a PhD, not researching Gato. I didn't know what I was at. I just thought PhD is the way to go. I got denied really quickly because it was clear from my statement of purpose that I did not know what I wanted to do, and I didn't even know what a PhD was or anything like that. So that year I lost I was outside of the application time period, whatever it's called, I forgot. So when I applied the following year, I was told that, hey, you're a biomedical engineer, you're applying for electrical engineering, and your grades are pretty bad. So you're in conditionally. So you need to make a B or above on all your classes within the first semester. And you also need to take, I forgot what they were called, filler courses. Basically, I had to take 4 electrical engineering courses to show them that, hey, I can do this. And these were undergraduate courses. They were, microprocessors, EM waves, digital logic, and I can't remember the last one. But I had to take those. So hence my master's took about 3 years instead of 2 years to finish, because I took a year to take those classes. That was really it. When I applied for schools that were not my alma mater, so outside of Texas, I was not really getting good responses. So essentially, I was getting basically rejected anywhere else I was applying. I understandably so. So I told myself, all right, let's just do it over whoever accepts me, I'll just go over there. And then in the future, I'll fix it with either another master's or a PhD, or maybe I don't even need it. Who knows? So essentially, that was my experience with it.
Awesome. I think the word you were looking for was leveling courses.
Yeah, 11 courses. Yeah, sorry.
Right. So Danger, they ask, so as an undergrad who just finished their second year, they're still not certain exactly what they want to focus in, since their courses haven't given them, enough insight in the industry. And so they're wondering what they should focus on, whether it be things that sound cool or titles on LinkedIn or research related to the specific field that they think might be cool.
If you're a sophomore, if you're not unsure where you want to go, I think one good thing you can do is go to these student organizations. There's not, I wouldn't say the big ones. I would only go to the big ones because they're usually just bring a speaker in and that's it. I know that in my school we had a lot of student organizations where they were working on projects, and there were student organizations where there was a lot of more focus on, getting companies to come in and actually talking with them, with actual engineers rather than like their business partners. Going through these organizations, I think, helps a lot because you're exposed to people your age looking at different things. Don't look for titles. Don't look for titles. Don't look for what's cool. That's where, I'm in computer science right now, and I don't like how a lot of people just are in the program because they are saying computer science is the thing to be in and machine learning is the greatest thing ever, right? And so what happens is that a lot of people are getting burnt out. They don't really like it. They're just in there because it's cool. It's what everybody's talking about. That can happen to you. What you need to do, I would say, is essentially go to these different organizations, go to the career fairs, look at the companies, look at what they do, and also see if you can attend conferences. There's a lot of free conferences online that you can attend within your field or even outside your field. And if you talk with professors and you say, "Hey, I'm really interested in this conference," they usually have a way to get you in for free if it's some sort of paid sort of conference. And so I also would suggest now with access to like things like Reddit and Discords like this to ask around and join different groups. Like right now, I have I don't know how many groups I'm in. I have in like mathematics, robotics, so forth. And I just scroll through them and say, hey, that looks interesting. I ask questions about it. And if I realize that, hey, I'm thinking about this more than I have for other subjects, then I know that's the sort of field I want to be in. But definitely look through conferences, possible conferences, look through career fairs, look through student organizations, and really just start talking with people. Don't buy into hype. Don't buy in for titles. Don't do a master's because it's a master's, or don't do a PhD to be called doctor. You really have to have the interest, or you're going to be miserable, essentially.
Good answer. Schrodinger's mouse is one of the questions that I missed earlier. They're asking, do you think it is necessary to start grad school right after the bachelor's degree, or should they get some kind of experience at work and then sign up for grad school?
So one thing I've noticed, and actually I was talking about this yesterday, don't go into a master's if you have no experience. Let's say you have no experience, no internships, no research, nothing outside of bachelor's. Don't go into a master's thinking, all right, once I'm done with the master's, I'm coming out with experience. If you're going with no experience, you're coming out with no experience. Master's is just courses. You're just doing some courses and that's it. If you do a thesis, it's a different story. So, for instance, I would suggest that, if you're not dead certain that you want to do a, academic career or research career, if you want to feel things out, it's best to, if you're able to get a job outside of, after your bachelor's, it's worth it to actually work in industry maybe for a year, maybe two, get some experience. It actually will help your application for grad school too. Fill that out because the industry world and the academic research field is two totally different animals. However, you can merge them if you play your cards right. So I wouldn't say it's, necessary to go grad school right after bachelor's. I think if you're not really sure, wait, see if you can find a job outside or not. If you can't, do go to grad school if you can. Apply as soon as you can, and apply for a thesis-based program. So that when you actually, because a thesis makes you work as an engineer, you have to go through. You have to read different papers. You have to understand what you want to do. You have to understand how you're going to approach the problem. Explain your results, publish your results. So now you have something physical that you can present to interviewers when they interview and they ask you what do you know, essentially. So if you are not dead certain on grad school, go to industry if you can for a year or two, feel it out. Some people say this is exactly what I want, and they never go back. It's never too late to go to grad school. My boss right now, he is doing his PhD. He is 47. One of my professors, when I was doing masters, his grad student was 52. So and most of the people I know that are doing their PhDs right now are roughly around 38 years old, 40, some of them 35. So there's really no age limit. You'll even find 25-year-olds doing their PhDs. So don't really think about, I'm losing time or stuff like that. Think about exactly how do you see your career playing out. Do you really want to sit here and stress out over technical things? And are you, walking around your house and you just can't get over this one thing? It's one problem in your head. It's just killing you. That sort of thing is some indications that, hey, let me go try out grad school. If you're working and you go into grad school and they're paying for it, try it. Maybe after 2-3 classes and a semester of your thesis, you don't like it. Leave. You have a job. If you don't have a job or anything like that, I think it's worthy to go to grad school though, with a thesis.
Touching on the topic of thesis masters, Schrodinger's pig, or AKA Rowan, he's asking that his school is giving him 2 options, whether to do a project or a thesis option. And he's wondering if it's worth it if you're not doing a PhD.
So I'm not sure what project master is, but if that's in reference to what I'm doing, yeah, it's the thesis. A thesis is much tougher because a project is just what a project was like. What I meant by project is like it's just course projects that I went the extra mile just for my own sake. A thesis is more like you're basically working for the professor. He wants results or she wants the results, and by a certain time, it has to be good, publishable. So you're expected to have a working system by the end of your 2-year program, and so that's kind of like an actual job essentially. A thesis requires you to be able to read different papers, analyze research papers, which is sometimes if you look at if anybody that does research, you know that out of 10 papers, only like 2 of them are written well. The other 8 are extremely hard to just get your skull through because they're just written as if like you're part of their team that did the experiment. So is it worth it if you're not planning to do a PhD? I tell everybody master's is worth it. Now it may help you or not, but there's no negative side to it. If you do have a job, obviously apply for it, get them to pay for it. Either you finish the master's and nothing happens, and you just carry on with the same life you had, or you finish it, you get promoted, or you have better job opportunities, which is what happened for me. I basically had when I was applying for jobs after I finished the master's, I was essentially seen more for the roles I wanted to go into, because grad school essentially tells a hiring manager, this person can take a complex problem, break it down, and get to a solution. That's essentially what grad school is. It's not specializing or anything like that. Just on a side note, like for example, if someone that does a PhD, let's say in protein folding, for example, that doesn't mean that's their life forever. Usually is, but a lot of people in grad school, when they do is they take those skills and they transfer it to something else during their fellowship. So that person doing protein folding algorithms, they can go and do it for something else, and they can take those same skills for another field. However, it's not that common, but it doesn't mean that's the end of be all. So do the master's if you have a job. If not, I think it's helpful to gain some experience if you do the thesis portion of it. I think that was the whole question. Either the project opportunities. Yeah.
Right. One of the last questions here. Bawarchi Kana asks if what advice would you give them for, they're a senior in electrical engineering with a relatively okay with GPA, which would be 3.6. That's actually a good GPA. But they have no experience, skills, or internships under their belt. So what advice would you give them?
Okay. So there's either 2 things you do. One is if you are in a position that you're able to do a master's, obviously, like I just said, do the master's thesis option. That's essentially giving you experience and skills when you come out. If you can't do that, there's people that just don't have the opportunity. Maybe family gets in the way, finances. That's all understandable. So not everybody's going to have the same luxury. And so if that is the case, what I would do is essentially what I am doing right now for my battery stuff. I go on Google Scholar. I look for, if I know exactly what I want to do a project on. I just don't know what project to do in that field, but I know it. I know the field. Sorry, let me rephrase that. I know the field I want to work in. I don't know the projects I want to do, but I know what kind of skills I want to apply for it. I essentially type in those keywords. I try to find out where it's applied within this field, and I try to replicate projects. And I also look at different projects on YouTube. People talk about, like, for example, like I do power electronics. I type in how do you actually design a buck converter, right? And there'll be a guy that is explaining, on MATLAB, do this and do some of that, and then take this Arduino, you code it up like this, and I basically replicate what they're doing. And I try to understand what they're doing as well. And I will put that on my resume. I will say, hey, look, I've worked on this. This is the skills I've learned through this project, essentially. So you would have to essentially come up with projects on your own. That doesn't mean come up with a new project out of nowhere. More so just replicate things. Try to, if you have the finances, at least to buy, different parts for electrical equipment, like power supplies and stuff like that. Always actually have a eye out for like DigiKey and stuff. There's a sale recently doing like 12-volt power supplies for like 18 cents because they need to get rid of them. So those kind of sales exist. So take advantage of that and essentially work on projects at home, either through simulation or through hardware, and try to just tinker with it, see what happens. If you don't know why something is reacting in some way, take that question, put it on a forum, Stack Exchange, Reddit, see what they say, and see if you can understand why it's, if someone else can explain it for you. And so from there, you're basically teaching yourself these skills. And really, if you did have an internship and you had a job, and you were in this job and you had no experience, you'll be doing the same thing. You're going to be given a task and you're like, hey, I've never done this in school. What the hell? How do I do this? And so what you're going to do is essentially talk to all your coworkers. Hey, how do you do this? How do you do this? How do you do that? Well, and you're basically going to be doing the same thing anyways, even if you were working. So that's sort of really the only options you have. Either you go into grad school for a thesis or you work on projects your own by replicating previous projects, at least just to get a start. Once you actually replicate enough projects, I think you're going to get into a position where you know exactly what the next project you want to work on is, rather than just doing random things.
Another question by Short Underpaid, aka Rowan. He's asking, what advice would you give someone who's still in school with no internship experience? Is it okay for them to apply for 10 jobs a day, or because of COVID, it can be hard, to get an internship? And so, what advice would you give them?
If you're still in school with no internship experience, if you're still in school with no internship, keep applying, but definitely keep applying more than 10. So I never applied for internships. I didn't really, sadly to say, I didn't even know they existed at the time. That's how oblivious I was. But for finding a job, I was applying like 50 to 100 times a day. Just randomly. I had the little LinkedIn quick apply, and I was just basically spamming it. If you can't find an internship, look for research positions within the school. There's a lot of, basically every professor will have work for undergraduates. So if you actually go to the website of each professor, and you type in the people in the lab, you have your PhD students, you have your master's students, and then you have your undergrad students. Definitely that's another good outlet you can go into. Internships is, held higher than, research in the terms in the eyes of HR. However, it's better than nothing. And if you have a good research lab and a good research professor, you will get basically the same skills, even more sometimes. So I would definitely start looking at all the different professors, not just in your department. So if you're electrical, I'm assuming you're electrical, don't just look at the electrical department. A lot of the people in the mechanical department might be doing stuff that you're doing as well. Because there's a lot of cross I guess I don't know the word cross contamination between a field. So they might need help with the EE side of things. For example, in my school, one of the professors was working on optimal control for underwater drones. So they had the mechanical side down, but they needed someone to actually implement this onto hardware, and they were looking for EEs. Even though this is the mechanical department, everybody in the lab is mechanical or chemical. They needed EE because they didn't have the time to spend on this to put it onto hardware. So don't just look into your own department. Look outside. You can easily find a research field, a research position like that. And if you do want to go that route, definitely reach out to the professor ahead of time and ask for a meeting. Sit down with them face to face and basically tell them why you want to be in that lab, why that specific lab. And essentially, one good thing is to always read about their work ahead of time and tell them, hey, this part of your work really interests me. I would love to be, if I can work on this with you or help you on some parts. And what they will do is basically give you a small little aspect of that, and they'll help you.
All right. Diamond Hands, he's asking, he wants a company like Lockheed Martin to notice him. He has developed a device for them in the past that was actually planned to be implemented into their facility. He's gone to many career fairs trying to get connected with employees, and he's gotten referrals, and he's applied for the posted jobs, but he's never gotten an interview. So what advice would you give him?
I have to agree with him because I applied to Lockheed more than I want to admit, and I don't think I even got rejections. Their application is probably still open or something. Lockheed specifically, I don't really know. They operate very differently than what I'm used to. I work for Jacobs, and anything similar to Jacobs or contractors, I could help you, but Lockheed is its own beast. I don't know if I have the information on that. Let's see. If I had to say something, maybe if you can find the HR on LinkedIn or employees that are in the same position as you, but I don't think that'll help. I'm pretty sure you've already done that too. Lockheed is it's a little stressful. I don't know if I have an answer for that.
They are a tough one. I have the same experience.
Yeah, I can't. I don't think I've ever got a response from them.
So if anybody else has any questions, feel free to type them in the chat. Give them just about a minute more, I guess. Someone's asking, are they allowed to reach out to you?
Yeah, sure. Yeah, go for it. Actually, we may be getting positions open, internship positions open. I think the internship positions, it's hard because the the engineer that opens them, he usually knows who he wants beforehand, but sometimes he does not. But I know that I think we're going to be opening more positions as well in the battery testing facility if anybody's interested. When it's going to be open, I'm not sure, but I know we have to do it because we need people. And we are getting more funding because of COVID being sort of, I guess, mitigated at NASA. And so, are you a particular type of major? No. Any major can reach out and any major can apply for the position that we're in. A lot of my coworkers typically are all chemical engineers, mechanical engineers. And actually a lot of the work I do at work is mechanical. I'm doing like CADing stuff. However, there's a small group of us that are electrical and, we do everything. Sadly for the same pay, but, it's very diverse in terms of the fields we work with. Actually, I think my boss, the one that's doing his PhD, is doing his PhD in psychology. I don't know why, but, there's people that are all different majors, all involved. So what about chemical engineering? What about it? If you're asking that I work with them, yes, every person that is a subject matter expert at my department is a chemical engineer, because we're working with batteries. what year of your graduate degree did you have to juggle with a job and virtually no sleep? My first 2 years, and that's not common because the job I had the first job I had was it's very uncommon. I was working night shift in the hospital, 12-hour shifts. And because of the amount of people, the small staff that we had, I had to work more hours than I should have. And so, yeah, it's not common at all. Working during graduate school is very common, specifically masters. Typically, master's students are either international students or working students. It's not really it's not really meant for students that are just sitting at home. So you basically fit in within that. But for me, I had a weird situation where I was working in, I was doing work with heart surgeries. And so I was working the cath lab and the OR room with, ICUs, CVOR, going through patient rehabs and stuff like that. So it's just a weird experience. I don't know how I ended up there, but, that's essentially the little period of my life where that was kind of a little odd, but yeah, don't worry about it. It's very doable. 2 classes per semester plus working full time is very doable. It sounds like a lot, but if you take advantage of the time during the weekends, that's really all you need. I think, I guess no one's really asked this, but I think it's a good point to say that graduate school is not difficult. Undergraduate is. Undergraduate, it's structured so that they're basically giving you a very hard program so that when you go into the field, you're ready. Graduate school is saying that, hey, they've already passed, they've shown they're able to do engineering, and now they're going to specialize in something they actually like. When you're specializing into something that you like, it becomes an easier class. And typically, it's not graded as such. When you're in grad school, you're not graded harshly. You're essentially, you're there just to learn. The grades are just, bureaucratic stuff for the school. The professors have to go through with. They have to have a grade for something, but you're not really there to prove that you can be an engineer anymore. You're there to actually learn, and so really. Maybe in the future this will change, but for now, schools, the metric used is grades. So there is still grades and stuff, but yeah. Those slides of numerical models are taught more or less in undergrad. I think that depends on the school. I know that most engineering degrees in undergrad, let me see if I'm still screen sharing. Yeah. A lot of these are partial differential equations. That's basically all it is. However, the control theory stuff, any of these or any of this optimization work, or anything here, all these MPC stuff or control theory, that's all graduate school. You will most likely not see that in undergrad unless you go to some places like MIT or University of Colorado or I forgot the name of the university, but it's in Australia. They do all this stuff in undergrad, which blows my mind. But PDE stuff, yeah. Don't mind if I speak. Yeah, go for it.
I probably missed you on the previous question when it comes to numerical models. So I saw 2-dimensional array. So for example, what are you using here? You brought up PDEs. Let's start there. Where would that be? Is it do you PDE? Right there.
So what is your question exactly?
Yeah, or rather, go back to the brain model again. Go back to the brain model. Yeah, okay. I noticed. Is that a recursion on the left side? Because I noticed there's a little loop.
Yes, this is a closed feedback loop.
And I mean, what method is this? Because I want to say it ties into Newton-Raphson, but or a series Newton-Raphson because I see iterate subtitles, but I'm not sure. Yeah.
So I guess if we go into details, this is basically your basic control system. You have a model of your system, your plant. You have a input. In this case, it's just SK represents the noise in the environment. Since we're working with human models, SK represents just anything outside of what's in our brain. So this is a model that describes the evolution of a person's emotions. The next block is an observation equation. So ZK and P of K represents the continuous features and the binary features. So we're saying this is the inherent or internal state of our brain, representing the valence. So obviously we can't measure emotions, right? We can't put a multimeter and say that's what emotions is, right? We need to have some sort of metric for it. What is our metric? We're using the continuous and binary features of our muscle signals, EMG. So that's our observation. So based on observations, we use it's a thing called mixed filter. It's a Kalman filter that does both continuous and binary estimation. We're estimating what is the valence or emotional state of the person based on the observations we just had. So we extract observations, we estimate it, and then we input it to our controller. We use the fuzzy controller. So this is the set theory. And essentially based on the output or the state that we estimate, we say, all right, act accordingly. So U of K is the control effort. That means this is what the control would do. Now, this part requires its own side of research. What is this control input? Maybe dimming the lights will help someone calm down, or playing a certain favorite music for a specific patient will help them calm down or excite them. So whatever U of K is, that's dependent on its own research. And then we feed this back in saying, okay, so the last time step, we excited the patient, the valence fluctuated like so. Based on that information and every information we had before that, let's do it again. Basically, we do the same loop again. Observe the current state, estimate the new state based on previous information, go back to the controller and keep doing this. Everything else you see here is actually it's a setup for this. So this brain model requires estimation for its parameters and states, because it's like if you have y equals mx plus b, how do you actually get what m and b is? You actually go through the plots, you look at where intercept is, what's the slope. Over here, we're looking at this and saying, all right, based on the data we have, can we extract the values of each one of these parameters? And that's what this is. This is another recursive thing. It's expectation maximization algorithm.
Yeah, I noticed lowercase sigma square. So you're using statistical information, right? Like you're grabbing variance, right? Okay.
Correct. This is a mixture. Well, it's called a mixture of Gaussian mixtures. So yeah, basically you're looking at distributions, and so based on distributions and how they overlap and how so basically the expectation step finds the expected value. And the M step finds the maximum likelihood of that value being part of this distribution. And so obviously if it's very likely that state is within this distribution of our valence, then that's the correct parameter value for.
Wait, what you mean by Gaussian? For the variance, right? You're talking about variance or the actual E step?
So I'm talking about like, you assume a distribution for each one of these parameters,
right?
And the E step basically calculates the expected value for the current state that we're measuring within their respective distributions. So we assume something. We assume like a Gaussian distribution for each one, and say, all right, from our measurements, what is the expected value in each one of the distributions? And then we go to the M step, which does the maximum likelihood. What is the likelihood of that value being within that distribution?
You're using the Gaussian being in other words, normal distribution, right? You're using right, and you're using that. I assume because you have more than 30 samples.
Oh, definitely. Yeah.
Okay, that's when it's safe to use normal.
Yeah.
And for the observation question, that's just you mapping what you observe from the EKG, right?
Yeah, the MG right here.
You're just mapping it onto the graph. You're not actually using it to model your brain model. That's for the mixed filter, right? Like that.
So we're not okay. This is more. So this is more. Have you taken any classes called state space by any chance?
Yeah, I'm not there yet.
So state space is basically a modern control method of describing a dynamical system. You say I have a system model which is explaining the states of where I am, and then you have an observation model. Observation is the actual sensor. So if I have a water heater, the tank is the system. The temperature of the current water is the state of the water, and then the sensor measuring the temperature is the observation, and that is fed back to a controller or you, for example, turning the knob based on, hey, I need to go hotter or colder depending on your goal. And so here we're doing the same thing. Our state is the emotions. We're measuring it through the EMG, and so we're using the observations to estimate what this is, what this state is, because we can't actually measure the emotions. So that's what this is a state-based approach to emotional control, more in a more, I guess, professional way of saying this. We're developing state-based models to transform our numbers to a state plane, and then from there we can control our.
Also, it's not so. Okay, so you're actually modeling using using the observation equation. So it's not like you have. It's not like you're grabbing EKG data and then you have the brain model. Like you're not comparing different models. You're still using the same one.
Yes. Yeah. Oh, exactly.
Oh, okay.
Yeah. This is real time. This is what once we're actually going to implement this pretty soon on actual hardware. This is going to be real time. Anything inside of this TV, or in this case, it's a TV, but we're picturing a watch, is real time application. So this is a difference between computer science and control theory. Control theory is model based. Computer science is data driven. So in computer science, what you would do is basically based on all the values you get over here, you develop a model based on the data. And so it doesn't really have to represent the dynamics. So you can have something like, in this case, it's very similar. It's the autoregressive function. However, if I was to do this for the battery stuff, we would not be using these dynamical equations if I was to do a data driven method. In machine learning, basically, none of this really matters. This is all a black box, and we say from their data, we use, let's say, a lasso regression or ridge regression method to get a model, and it will just be like random numbers times different feature values, and that will be your model. It doesn't really describe the dynamics. It's based on the data. What my field does is we work on the actual dynamics of the system. We look at the differential equations that define a system, and based on that, we do our predictions or controls or anything like that.
But it does require you to identify the dynamics itself. But
for our case, yes. So if you're doing control, you are looking at dynamics only. They are there. So in the future, what I'm going to is called a learning control, which is machine learning plus model. So you're using both data and using models. You're using the data to reduce the model order correctly, and then using the model to actually regulate and perform any tasks. So if you look at go ahead.
Because I figure you use machine learning if you have a hard time understanding the dynamics, say neural system, for example. So you might understand how two neurons work and vaguely understand a couple set, but the holes beyond us, you might want. So you might go from that avenue. But what I figure here, the dynamics, so I guess it's more optimal, or it's easier to optimize to just directly apply it. More or less, right?
I want to say easy, but yeah, it's more representative. I would say
right.
It's more representative.
Yeah.
So if you look at
you might be able to get more representation from machine learning, but that probably take.
Yeah, you need terabytes over terabytes of data. You need years and years of data to prove to say, hey, yes, this model will work over different loads on our system. So different experiences that our system might have, we can predict it based on this one model. But usually what you see in machine learning is that you have multiple models for different situations. If you look at SpaceX and how they land plane or the rocket, or how Tesla moves their cars, or how these drones fly themselves with what Amazon is doing, or like how Boston Dynamics those like dancing robots and stuff. I don't know if y'all seen those videos. That's all through controls. That's all through basically well, minus the robots, but like something like the rocket or the self-driving cars. We can't really rely on machine learning only. We have to know the dynamics of the car or the rocket because of all the external features. We can't risk anybody dying in those situations. So we use control theory and model-based design in those kind of situations. Same thing for me. Batteries, it's too risky. We are not okay with just using just pure data and say, yeah, the batteries will be fine over the next 10 years. We saw what happened with Samsung and maybe in the future, or actually with Tesla too. Some of their cars caught on fire because of the basically using bad battery algorithms that were based on just redundant data. So yeah, there's a big difference in there, and there's a lot of overlap. And it's a pretty new field, so hopefully anybody's interested, let's talk about it more.
Sorry for that. I took a lot of time.
No.
Hey, Swayze, are you want to call this or?
It's really up to anybody. I'm free, really.
Okay, we have, I think, a couple of more questions here.
Sure.
I'm looking real quick. From Chun Snow. Maybe that's how you say their name. They're asking, what are your thoughts on the fuel cell industry? And do you think it will grow or has potential applications in your field?
Fuel cell. Say that again, sorry.
Yes, he's asking what are your thoughts?
What we're looking towards is more so solid state batteries. That's what I'm hearing more of than fuel cells and glass batteries. So basically perfecting the lithium ion so that we're not using liquid electrolyte. We're using some other sort of substrate. So we're using either solid or glass instead. But fuel cells, I'm not really sure of. I hear it a lot, but I just haven't had time to look into it.
Next question is from Chase, and he's asking, have you been made aware of how your work or research has been utilized or cited?
Have I been aware of if it's been...
Right, if your work or research has been utilized or cited. He goes on to say that he's reminded of an engineer that wasn't aware that his designs for protecting Windows on the ISS until a YouTuber found him, and he wasn't aware that his work was being utilized.
No, no, I'm not aware. I don't have anything worthy of citing. But if they were to do it and I didn't know, then whatever. To me, that's not really important. As long as it works and for someone, then that's fine. I'm not really concerned with anybody stealing my work or being recognized for it. But up to this point, I should only really have publications from the undergraduate research, and then hopefully soon for the emotional stuff once we're done with the actual project. A lot of things I've shown you still needs work to be on. So.
And speaking of your work, somebody asked if your PowerPoint would be available.
Yeah, sure. I can provide this PowerPoint and anything else really. I have a few slides. I have PowerPoints for all these projects, and I'm open to talking with anybody about the experience stuff as well. Obviously, I'm not exactly the be all know all on this. So I'm pretty sure in the future when we have more talks, there's gonna be different views, and some people might have better advice for career development and stuff like that. So as long as you're able to take what everybody says and figure out what you want for yourself, that's what's important.
All right, so we're gonna call it at two more questions. One is from Ada. She's asking, how much of your studies have you applied to your field?
How much of my research has been? Sorry, I was reading two different questions. Sorry.
Right. She's asking how much of your studies, presumably in college, have you applied to your field?
Oh, I've applied none of my undergraduate except for what I learned in the research project. I'm applying and still am everything I've learned in my master's, and that's what I wanted to do. That was my goal. So I didn't want all the trouble I went through to get here to go to waste. So I'm actually using all of it, all my master stuff currently, and actually the stuff I'm just learned in my computer science class I'm already using as well. So the thing is that you might fall into a position where you're in a position like me. You're in a facility like NASA, and you have this sort of job. There's a lot of my coworkers. I think almost all of them. If they're not proactive, they can be doing the same exact thing every single day and never apply anything they've learned. So a lot of them do just write test procedures, test plans, get things signed, and repeat it every single day. I don't have to use any of this stuff. Battery algorithms and stuff was not part of my work description when I applied. It's something I was like, I really think that the department will benefit from this, and so I will do this on my own time, present it to them. Now that they like it, they're open for me to actually use it. So I've basically opened this opportunity for myself, and I think everybody else should try to do the same thing in their own workplace. Just because they're not using it, just because those techniques are not being used, doesn't mean it doesn't work, or the department knows about it and doesn't want to. Usually, what the case is that they don't know. They don't know you can't do that, and if they do, that's better for you because now you get more information. Oh, that's why you don't use this kind of method. Oh, that's why you don't use these skills. So you really have to try to open those opportunities for yourself through just proposing ideas and stuff to your team, and eventually you'll either be in a position where you're able to use those, or you'll find out why it's not being used, and that's also really good information.
In terms of your studies, Spooky or SPPKY asks, did you ever cover the ethics and philosophy of advancing tech into areas of one of the topics you were mentioning? This was asked earlier.
More so when it comes to like medical stuff, yes. Battery stuff, space stuff. I mean, I don't know what the ethics would be, but especially for something like emotional control, which sounds like some Big Brother stuff. Yes, there is discussion on it. How do we actually go about this so that it's not seen as something like, we're not infringing on people's life, and we're not controlling them literally. And so, yeah, the ethics it's huge. But we're only doing this as simulation and a proof of study. I think we're not at the stage where if we were to implement this, we would have to actually discuss this with, I guess, would we probably be tech lawyers that we have to talk to and see where this stands. But at the moment, I personally haven't done it, but it's something that we just talk with each other in a group, especially for that project. Because it seems weird when I tell people that, we're going to help you control your emotions through technology, which is crazy. Even when I say it right now, it freaks me out. But being able to explain it to in layman terms and show people that they're the ones in control and they're the ones that are regulating themselves is what the work has been. And so maybe one day we'll get there if everything works out. But yeah, that's very important, and more so medical stuff than things like batteries, for example.
Okay, and the last question is by JNE. They write, I saw John B. Goodenough, the inventor of Li-ion battery chemistry, developed a glass-based battery technology. Have you done any research into that technology? And if so, what would be its potential advantages and disadvantages when compared with Li-ion? I'm not sure if I'm saying that right.
Lithium ion, yeah. I know John Goodenough. He actually comes over sometimes to sort of discuss what he's doing, and basically he's really good friends with two of the subject matter experts at other departments. So he comes and visits. He also presents a few things with us. He's developing the glass battery technology, which I was just mentioning during that fuel cell question. But what is the potential advantage and disadvantage? Disadvantage, it's new. No one really knows how it will work, except for good enough. But maybe it'll just be good enough. The advantage is that we're not using liquid solutions we're not using a liquid solute in the battery for the transport of lithium ions. We're using solid. Essentially, it's another version of solid state batteries. Glass is cheap and is resistant to the mechanical stress that we see with what we have in our current batteries, and so that's where the advantage comes in. When you have solid, so you have a solid interface for the lithium ions to go back and forth in the battery. What you're creating is you're creating more surface area for so you can package more lithium ions, so you get higher capacity in your batteries. And also what you're doing is you're reducing the side reactions. Side reactions are the inert chemicals that make up the liquid solution are not there anymore. So they're not able to snag the lithium ions as they're transporting. So you are able to increase the life of your battery as well. So really, those are the main advantages. And it's also safer. When it's liquid, you really can't predict the behavior of what's going on.
Okay, Sways, on behalf of the STEM Network server, we want to thank you for your time, for sharing your story and answering our questions.
Hey, no problem, anytime. And if anybody has any questions, just reach out to me, either on Discord, DM me. And if the jobs open up, I'll definitely post it. I posted it before, but when I posted those, I realized they were already taken. So I actually heard about them pretty late. So if I ever find any openings, definitely I will reach out to Discord and see what we can do.
Great. Again, thank you, Sways, and for the audience. If you would like to share your story, please contact one of the admins or mods, and we can help set up that presentation for you. And again, just feel free to share our Discord link with everyone that you know. And on Reddit, you can find it in the server share tab, I believe it is. And as well as a reminder, this presentation, after the presentation is over, it will be posted, the link to the YouTube page. I'm getting my words mixed up here. The YouTube link will be posted after the presentation. And thank you.
Sounds good. And thanks for having me.
And everyone have a good night.
Yep. Take it easy.